Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Green beyond gravity. Cultivating plants in the cosmos. The dream of cosmic cultivation. The dream of cosmic cultivation is a tale as old as space exploration itself. It's a story that begins not with seeds and soil, but with the human spirit and its unyielding desire to reach beyond the familiar confines of Earth. The concept of growing plants in space has always been intertwined with our visions of the future, a future where humanity is not just visiting other planets, but living on them, making them a new home. This dream took its first steps towards reality with the advent of space travel. As astronauts orbited the Earth and walked on the Moon, the question arose: could life from our planet thrive in the void beyond? The answer lay not just in the survival of humans in space, but also in the potential companionship of plants. The benefits were clear. Plants could provide sustenance, recycle waste, and offer a semblance of Earth's environment, a touch of green against the backdrop of the cosmos. The challenges, however, were daunting. Without gravity, how would plants know which way to grow? How would water reach the roots, and how would air circulate around the leaves? These questions spurred scientists and engineers to think creatively, to reimagine agriculture for a zero-gravity world. In the quest to cultivate plants beyond Earth, one of the most formidable challenges is the harsh space environment, characterized by intense radiation, the absence or thinness of atmosphere, and the lack of a protective magnetic field. These factors pose significant risks to biological systems and have profound implications for the growth and development of plants in extraterrestrial settings. Space radiation and plant growth. Space radiation, including cosmic rays and solar flares, presents a constant threat to living organisms. Unlike Earth, which has a thick atmosphere and a magnetic field that deflects most of this radiation, space offers no such protection. On the Moon and Mars, plants would be exposed to levels of radiation that could damage DNA, disrupt cellular processes, and impair growth. To mitigate these effects, researchers are exploring several strategies. One approach is to use regolith, the loose soil found on the Moon and Mars, as a shielding material. By covering greenhouses or embedding growth chambers within the regolith, plants can be protected from the brunt of radiation. Another strategy involves developing genetically engineered plants with enhanced DNA repair mechanisms or increased tolerance to radiation, drawing inspiration from extremophiles on Earth that survive in high radiation environments. Adapting to the lack of atmosphere. The absence of atmosphere on the Moon and the thin atmosphere on Mars pose another set of challenges for plant growth. Without atmospheric pressure, water and other essential fluids can boil away, and plants are at risk of desiccation. Moreover, The lack of an atmosphere means there is no buffer to moderate temperature extremes, which can be lethal to plants. To address these issues, controlled environment agriculture (CA) systems are being designed to create Earth-like conditions for plants. These systems regulate pressure, temperature, humidity, and gas composition, providing a stable environment for plant growth. Inflatable, pressurized greenhouses with advanced life support systems are among the solutions being considered to simulate Earth's atmospheric conditions in space. The role of a magnetic field in plant cultivation. Earth's magnetic field is thought to influence plant growth through magnetoreception, a process not yet fully understood but believed to affect plant metabolism and stress responses. The absence of a natural magnetic field in space and on other celestial bodies means that plants may not experience these potential benefits. Scientists are investigating the possibility of creating artificial magnetic fields within growth habitats to study their effects on plant health and development. While the exact role of magnetism in plant biology is still being explored, the creation of artificial magnetic fields could be another tool in the arsenal for supporting plant life in space. In summary, the challenges of space radiation, lack of atmosphere, and absence of a magnetic field are significant but not insurmountable. Through a combination of protective measures, advanced engineering, and biological innovation, it is possible to create environments where plants can grow and contribute to human endeavors in space. As we continue to push the boundaries of space agriculture, the resilience and adaptability of life continue to inspire and guide our efforts. Pioneering plant growth in microgravity. The pioneering efforts to grow plants in microgravity environments began with simple experiments. Could seeds germinate without gravity? How would roots navigate an environment where down is an irrelevant concept? The answers to these questions laid the foundation for what would become a sophisticated endeavor to cultivate life in space. Spacecraft and space stations became laboratories for this grand experiment. The microgravity conditions presented unique challenges. Water behaved unpredictably, air failed to circulate properly, and roots struggled to anchor themselves. To address these issues, space agencies developed advanced growth chambers designed to manage these elements. These chambers, equipped with systems to deliver water and nutrients directly to the roots, became the first gardens in the sky. LED lights replaced the sun, providing the necessary spectrum of light for photosynthesis. These artificial suns were not just functional, they were symbolic beacons of human ingenuity, shining on leaves that had never felt the warmth of Earth's star. The veggie experiment and beyond. The vegetable production system, affectionately known as veggie, marked a significant milestone in space agriculture. Aboard the International Space Station, Veggie's bright pink LED lights illuminated the first crops grown entirely in space. Lettuce, zinnias, and even Chinese cabbage flourished under the care of astronauts, who became part-time gardeners in their orbital home. The success of veggie was more than a novelty. It was a proof of concept. Plants could not only survive in space, they could thrive. The fresh produce provided a welcome addition to the astronauts' diet, a break from the monotony of prepackaged meals. But perhaps more importantly, veggie offered insights into how plants adapt to stress, how they respond to an environment unlike any on Earth. These early experiments were just the beginning. With each seed sown and each harvest gathered, humanity's dream of cosmic cultivation grew stronger. The knowledge gained from veggie and subsequent experiments would inform future endeavors on the Moon, Mars, and beyond. It was a small step in the garden, but a giant leap for mankind's aspirations in the cosmos. Lunar farming, overcoming the Moon's hostility. The Moon, Earth's closest celestial neighbor, has long been a beacon for human curiosity and ambition. As we set our sights on establishing a more permanent presence there, the concept of lunar farming has moved from the realm of science fiction to a tangible goal. The lunar surface, with its fine regolith and lack of atmosphere, presents a hostile environment for traditional agriculture. Yet, it is within this very hostility that scientists and visionaries see opportunity. The regolith of the Moon is a powdery soil, the result of billions of years of meteorite impacts. It lacks organic material and is composed of fine, abrasive particles that can damage equipment and human tissue. Despite these challenges, researchers have found that certain hardy plants can germinate in this soil. The key to lunar farming lies in understanding and leveraging the unique properties of the regolith, such as its ability to retain heat and potentially provide some protection from solar radiation. To overcome the lack of atmosphere, lunar greenhouses would need to be entirely self-contained, with controlled environments to manage temperature, humidity, and air composition. These greenhouses would likely rely on hydroponic or aeroponic systems, where plants are grown without soil, their roots suspended in air or nutrient-rich solutions. LED lighting would simulate sunlight, and advanced robotics could assist in plant care and harvesting. The water necessary for these systems could be sourced from the Moon itself, extracted from ice deposits in permanently shadowed craters at the poles. This water would be precious, meticulously recycled and conserved. Lunar farming would not only provide fresh food for astronauts but also contribute to life support systems, recycling carbon dioxide and producing oxygen. Martian greenhouses. A red planet turns green. Mars, with its thin atmosphere and cold climate, is a world that beckons for transformation. The vision of Martian greenhouses is one of the most captivating aspects of our interplanetary aspirations. Unlike the Moon, Mars has a day-night cycle similar to Earth's, and its gravity, though only a third of Earth's, could help give plants a sense of directionality in their growth. The Martian soil, however, contains perchlorates, salts that are toxic to humans. Any attempt at farming would require the removal or neutralization of these chemicals. researchers are exploring various bioremediation techniques, including the use of bacteria that can break down perchlorates, making the soil safe for plant growth. Temperature control is another critical factor. Martian nights are frigid, and even during the day, temperatures rarely rise above freezing. Martian greenhouses would need robust insulation and heating systems, possibly utilizing geothermal energy or nuclear power. The thin atmosphere also means that plants would be exposed to higher levels of radiation, necessitating protective measures such as regolith shielding or magnetic field generators. Despite these challenges, the potential rewards of Martian agriculture are immense. Growing plants on Mars would not only provide sustenance for future colonists but also contribute to terraforming efforts, potentially altering the planet's environment to be more Earth-like over time. Genetic engineering for extraterrestrial flora. The harsh conditions of space, the Moon, and Mars require plants that are not just robust but also adaptable. Genetic engineering offers a pathway to creating such plants, tailored to thrive in extraterrestrial environments. By borrowing traits from extremophiles, organisms that live in Earth's most inhospitable places, scientists can design plants that are more resistant to radiation, extreme temperatures, and low gravity. These designer plants could possess deeper root systems for better anchorage and nutrient uptake, leaves with enhanced photosynthetic efficiency to cope with reduced light, and reinforced cell walls to withstand the rigors of space travel. The genetic modifications could also enable plants to recycle nutrients more effectively, reducing the need for external inputs and making them ideal for closed-loop life support systems. The ethical considerations of such genetic manipulation are not taken lightly. The engineered plants would be subject to rigorous testing to ensure they pose no harm to humans or the delicate balance of a space habitat's ecosystem. As we venture into the realm of creating life suited for other worlds, we tread carefully, with respect for the profound responsibility that comes with our expanding capabilities. The detailed exploration of these parts reveals the intricate tapestry of challenges and innovations that define the quest to grow plants beyond Earth. It is a quest that pushes the boundaries of biology, engineering, and human ingenuity, all in pursuit of a dream that grows ever closer to reality. Bioregenerative life support systems. The concept of bioregenerative life support systems, BLSS, represents a significant leap in our approach to long-duration space missions. These systems are not merely about growing plants for food. They are about creating a self-sustaining ecosystem that can support human life indefinitely. A BLSS integrates plants, microorganisms, and sometimes aquatic species into a closed-loop system that mimics Earth's natural cycles. In such a system, every output is recycled to become an input for another process. Carbon dioxide exhaled by astronauts is absorbed by plants during photosynthesis, producing oxygen. Water used by the crew is purified by plants through transpiration, and organic waste is broken down by bacteria to become fertilizer. This intricate web of life not only provides the essentials for survival but also contributes to the psychological well-being of space travelers by offering a living, breathing piece of Earth. Developing a fully functional BLSS is a complex challenge that requires balancing numerous variables to maintain equilibrium. Light, temperature, humidity, and nutrient levels must be carefully controlled to ensure the health of the system. Researchers are exploring various plant species and growth techniques to optimize efficiency and yield. The lessons learned from these systems have the potential to revolutionize sustainability practices on Earth, particularly in areas where resources are limited. The psychological oasis of space gardens. The psychological benefits of plant life in the confined and artificial environment of a spacecraft or habitat cannot be overstated. For astronauts, the presence of greenery provides a connection to Earth, a reminder of the natural world they've left behind. Tending to plants, watching them grow and bloom, offers a therapeutic respite from the stresses of space travel. Space gardens serve as a psychological oasis, a place where astronauts can engage in the familiar act of gardening, providing a sense of normalcy and routine. The vibrant colors and textures of plants, the smell of fresh soil, and the taste of just harvested produce can have a profound impact on mood and mental health. As we venture further into space, the design of habitats will likely incorporate green spaces not just for their practical benefits but also for their ability to create a more home-like environment. Earthly applications of space farming techniques. The technologies and methods developed for growing plants in space have far-reaching implications for agriculture on Earth. Controlled environment agriculture, such as hydroponics and aeroponics, has gained popularity as a result of space research. These soil-less farming methods allow for the cultivation of crops in urban environments, deserts, and other places where traditional farming is not feasible. Space farming has also advanced our understanding of plant stress physiology, leading to the development of more resilient crop varieties. The efficient use of resources in space agriculture is inspiring sustainable practices on Earth, reducing water and nutrient waste. As climate change and population growth put pressure on our planet's resources, the lessons from space farming could help ensure food security for future generations. The future harvests of the cosmos. As we stand on the cusp of a new era in space exploration, the future of space agriculture looks bright. The dream of cosmic cultivation is no longer just a dream. It is becoming a reality. The advances in technology and biology that have made this possible are not just milestones in our journey to the stars. They are beacons of hope for life on Earth. The future harvests of the cosmos will be the result of the collective efforts of scientists, engineers, astronauts, and dreamers. They will be the fruits of a civilization that refused to be bound by the limits of its cradle. As we look to the stars, we carry with us the knowledge that wherever we go, we can bring life, we can create, and we can thrive. The green shoots that emerge from the soils of other worlds are more than just plants. They are symbols of our potential, our resilience, and our enduring quest to explore and understand the universe. They remind us that life, in all its forms, is an adventure that stretches far beyond the horizons of our home planet. And as we continue to sow the seeds of our future in the cosmos, we do so with the hope that these distant gardens will one day flourish, offering sustenance and solace to those who follow the path we have blazed. The cultivation of plants in space, on the Moon, and on Mars is a testament to the indomitable human spirit, a spirit that thrives on the challenge of turning the impossible into the possible.